Good afternoon. I hope you all had a refreshing tea break and you all are ready for the next engaging session. On behalf of the organizing committee, it's my pleasure to welcome you all to the AICT Training and Learning sponsored 1 week offline faculty development program titled as Solar Effect on Climate Dynamics and Renewable Energy towards Sustainable Solutions, taking place from November 18 to 23rd, 2024. This FDP is organized by the Department of Applied Electronics and Instrumentation Engineering at Haldia Institute of Technology. Today we are privileged to have with us an esteemed speaker, Dr. Tamal Boshak, works as an assistant professor in Indian Center for Space Physics, Kolkata, ICSP, whose expertise and insights will greatly contribute to our understanding of sustainable energy solutions and climate dynamics. Before we proceed, let us welcome our speaker onto the dais with a huge round of applause. Now, let honor the dynamic personality on the dais with felicitation ceremony. Now, to honor our esteemed speaker, Dr. Tamal Boshak, I request Mrs. Shweta Bijoli, Assistant Professor of AI Department, to present a plant as a token of her respect and gratitude. Thank you, ma'am. Now I would like to take a moment to introduce the distinguished speaker for today's session. Dr. Tamal Boshak works as an assistant professor in Indian Center for Space Physics, Kolkata. Previously, he was an assistant professor at the Department of Physics, Amity University, Kolkata. After doing MSc in Physics from Presidency College, Kolkata, he completed his PhD in Space and Ionospheric Sciences from Asian Books National Center for Basic Science, Kolkata. He was selected for the U1SI INRASS Young Indian Radio Scientist Award in Asia Specific Radio Science Conference 2019. He worked as a postdoctoral researcher in the University of Electrocommunications, Tokyo, Japan. He published several research papers in international peer-reviewed journals and presented the works in many overseas international conferences in USA, Japan, Germany, UAE, Turkey, Portugal, etc. He is instrumental in popularizing space science and astronomy among students. So without further ado, let us welcome Dr. Boshak to lead this session on the topic Monitoring of sub-ionospheric very low frequency VLF signal, a systemized tool for remotely scrutinizing the D-region ionosphere during solar energetic incidences.
So, thank you. First of all, I thank Shomo for inviting me. Also, I thank Kaushik sir. He has been my inspiration for a very, very long time. So, what I am going to talk about is the monitoring of sub-ionospheric very low frequency signal, which is a systemized tool for remotely scrutinizing the D-region ionosphere and during solar events. So Kaushik sir already talked about the sun, what is dynamics going on the sun and all that. So I choose to come very closer to Earth and effect of the sun, but what is happening on the ionosphere and how we monitor it without going to the ionosphere. So this is my topic. So first of all, ionosphere is an ionized region, which is the upper part of the atmosphere, which starts from, for example, 70 kilometers and it goes up to 1000 kilometers. So ionosphere is divided ionosphere, as you can see in the picture, ionosphere is divided into several. Atmosphere itself is from troposphere, stratosphere, then mesosphere, thermosphere, and finally the exosphere. The troposphere is the sphere where we live in, and from other, as you can see, from 70 km and above over here, this the region which is ionized. You know, as the density goes lower, then the solar ionizing action that comes up, and this neutral, this full profile that goes, and then it becomes ionized, and this ionization and the degree of ionization and their property that gets changed due to solar, mainly due to solar activities, and there are other things which are going on. So before I go further, let us just discuss about what are the let us discuss about the other constituents. It's mostly nitrogen, then oxygen, and then a small amount of carbon dioxide. So small amount of carbon dioxide and all that. So this is our structure. So now because I concentrate on the ionosphere, so this ionosphere is basically have different layers. It's the lowermost layer is called D layer. Sometimes we call it D region, or sometimes we call it D layer, but this actually we mean similar same things. So D layer is the lowermost layer, and E layer is the next to the D layer, which comes from just above the E layer, and then we have F layer. So first of all I start with F layer, but however I will not go to the detail of F layer. I will concentrate on D layer, but F layer is very different layer, because F layer is, we call it F layer at the night time. As soon as the solar influence, it actually divides into two different layers. We call it F1 and F2. And layer means, I should mention here, layer means there are Chapman layers. So Chapman was the first person who almost like 78 years back, he actually gave the theoretical interpretation of formation of ionospheric layers with the influence of the solar irradiation. How the irradiation comes, and actually there is a tug of war between the ionization and the ionospheric chemical recombination. So there are some chemical equations, of course I am not going to the details of that, but there is like a balancing thing, and that results into formation of this ionospheric layer. And Chapman first gave this thing, and then this concept of D, E and F1 and F2 that came into picture. And E layer is a regular layer, and D layer is, there are very special properties about D layer. For example, D layer is a layer which is the only layer which is temporal. For example, when there is like daytime, for example we are in India, it is daytime, so the D layer exists, and as soon as after sunset there will be recombination process, and this D layer will, the ions and the free electrons in the D layer, they will be recombined, and as a result this layer will completely disappear, and in the night time ionosphere it will start from E layer. So this D layer, another property of D layer, it is the thinnest layer. This D layer actually starts from 60 kilometers and go up to 90 kilometers. But the most important feature is it is temporal. It is not, so that's why you can look at this picture, that this part is when sun is present, and this is like a schematic diagram, but here you can see you will find no D layer or D region, but in this case it is also temporal layer. But you will be surprised to know that there are, apart from free electrons and the nitrous oxide and oxygen and other things, total 6,000 kinds of chemical components are there, and most of them are called hydrated ions, so where the water components are associated. 6,000. So of course from maybe 99% of them are very rare to find, but they are actually existing, and during our satellite and other observations their existence was found. So first of all we will discuss that. Okay, so first I will, as you have seen in my presentation, that I am going to talk about very low frequency signals. And so very low frequency signal is a kilohertz signal, which is very low frequency, means its frequency range is from 3 to 30 kilohertz. So 3 to 30 kilohertz signal that gets reflected from the D region of the ionosphere. As you know that we are very famous about the radio communication starting from Jagadish Chandra Bose, that these ionospheric layers are famous for reflecting back the radio waves, and different signals having different frequency then gets reflected from the different layers of the ionosphere. So the interesting thing is that, so that's why that there is importance of different layers. For example, we use our mobile telecommunication device, those are actually, that works in megahertz to gigahertz signal, that gets reflected from F1 or F2 layers. But we are talking about the kilohertz signal, that is actually that reflected from the D region of the ionosphere, and actually it depends on the ion density or the chemical density and the conductivity depending on those factors. So first of all, before I go into this, so these things I already told. So before I go into this, so D region is sensitive to very low frequency signals. So before I should explain that why it is very low frequency is the only, not only the one of the few way outs to look at the D region. For example, D region is situated at 70 to 90 kilometers. So if we, for example, if we have a balloon experiment, as we in our Indian Center for Physics, we have our independent balloon program, but balloon maximum can go up to 40 to 45 kilometers. So D region is out of reach for the balloon experiments. So in ICSG we do stratospheric balloons. And again, the NASA and other, they have their satellite, but satellite that their altitude range is from 200 kilometers to 400 kilometers. So like the low orbit satellites. So the D region is only, and the D and E, for example, they are only void region of the ionosphere that actually it is not very easy to study directly, or using balloons or using satellites. So it's a way out is the indirect or remote study of these regions. So that's why this is the technique of the radio signal, and that what happens, there are some very low frequency stations that this is the picture, another schematic picture. There are actually very low transmitting stations, and this actually they get reflected from the ionosphere, and this also this ionospheric reflection of this. Again, I am not going into details, but how the ionized medium that signal reflects in presence of magnetic field and all, these are again explained by the Appleton-Harty theory. Appleton actually took into consideration all these factors, and they calculated what is the necessary electron density and other things are required for reflection. These are this diagram is of course it looks like a mirror reflection, but it is not. These are actually the total internal reflections which are taking place over the years. So this is just for the simplicity of the schematic diagram. So please excuse me for that. But this is the way. But what is interesting is that this very low frequency signal is a kilohertz. So you can have a very one-line calculation that if a signal having kilohertz frequency, what should be the wavelength? So for a kilohertz frequency, the wavelength is of the order of 10 to 20 kilometers. So we are dealing with the very low frequency, we are trying to analyze, these are actually 20 kilometers. So what is the idea is that in the distance from transmitter to receiver, that distance, that signal can travel through this like single or multiple reflections with like lesser amount of attenuation in the signal that can travel actually thousands of kilometers. That is an interesting thing. So what is the idea is that we have one transmitter, okay, and that signal that emits signal that actually gets reflected from the ionosphere. We have a receiver which is practically inexpensive, and we receive the signal, and as the ionospheric dynamics, I will go into this one by one, as that gets changed, the signal amplitude, signal phase, those profiles that get changed. So we measure this, and as associated we have our theoretical modeling. Using that, we can calculate the ionospheric parameters, for example. Not all, but few of them I will try to cover, like electron density and other things. So this is a very very cheap, and monetarily it's not much expensive, but that out with the help of theory, with the help of modeling, and with the nowadays with the help of, we are using also machine learning, other things, with the help of all these packages, these things are very efficient tool to look at the D region which was apparently a void region of the ionosphere to investigate. So this is the way, and now, so before I go into that, this is our okay, one thing before I look at this, explain this. So first I should tell about the very low frequency transmitters. So first of all, transmitter means it is traveling thousands of kilometers. So you should understand that these transmitters are have sufficient power. Okay, so one transmitter, for example, we have only one such Indian transmitter which is located at a place called Vijayanagara, which is very close to Kanyakumari. Try to know, if you don't know, that these transmitters are not at all for research purpose. These are actually Indian Navy transmitters, which is operated by Government of India Navy, and they use for submarine communication. That's why it is located near Kanyakumari, all around this ocean. Okay, so they actually send their coded information and they have their communication and all that. But what is our benefit is that we can, with a small amount of receiver, LC circuit, and we receive digital receiver filtering, we get this VLF signal, we receive this signal for free. Okay, so we don't have to pay anything, just you have to set up your receiver and software system, but signal we are available. I'm talking about Indian transmitter because I live in India, where there are all over, there are dozens of transmitters there in low latitude, equator, high latitude, even within the polar boundary and all that. So it's a free wave going on, free science opportunity is going on. So just you have to catch and you have to start your investigation. That's what we have started. So this is, so that's why, and of course the coded information we cannot decode because we were not allowed for that. For that we will be behind the bars if we do this. But the carrier signal, what we get is we are very happy to do the research with that, and we are very happy to investigate. Of course, the theoretical modeling is needed. So now I come to this slide. This is actually, we call it diurnal variation. So signal, what we receive, as we said that we receive the very low frequency signal. This is a plot for the amplitude profile of the very low frequency. So if you look at the x-axis, it is a 24-hour plot. 24 hours. So this starts 0 means you plot it in Indian time. And this is 0 means the midnight 12, and again this part is also will be less than. So this is the signal. This is basically the, here you can see some irregular type of variation. What is the gross profile? What we see is irregular type of variation. Then we observe a very good regular profile. Then again, so what is that? It is a night time. Then it is this, we technically call it a solar sunrise terminator. Then we have like this is called as you know, after sunrise, what happens? The actually sun takes the control of the ionosphere, of the entire ionosphere. So what happens? At the ionization in the profile increases, then their amplitude profile becomes regular, and this is the noon time, as you understand. And then it is sunset, and after sunset there is irregular profile, apparently irregular profile. Because after sunset there is no sun. That's why what happens, the atmospheric gravity wave and the local factors that are dominant, and there is some. Of course, if we do statistical analysis, then of course we get many good results we have. But apparently, if you look for a single day, you will see that night time is like kind of irregular. But daytime is actually very varies the like solar zenith angle profile of the sun. So this part is interesting. We call this part is white day. White day defines that there is no other additional solar activity like solar flares, as I was saying, it was going. So this part, next part, it is called solar activity. Active day means the other than regular activity, different things are going on. So as you can see that these are C class, C and M are the different classes of solar flares. Those are happening, and those are actually, those are causing the additional ionization in the entire ionosphere. So this, due to this additional ionosphere, as what happens that as the additional ionosphere comes up, then what will happen actually in physics, if I say a little bit, then the necessary electron or ion density which is required to reflect back the VLF signal, that becomes available at relatively lower altitude of the region. So the effective propagation path or effective signal traveling path gets changed, and as a result of that we observe this perturbations. For example, I am showing you the amplitude perturbations, amplitude signal, but there are phases which I am not going into that, but those are very similar. So what is the advantage of this? So as Sir was saying that, okay, if we have satellites, Sir was saying, oh, NASA and NOAA, if you go to that satellite data, you can actually easily, you can see the X-ray profile of solar flare and all. So but if you have a VLF device and a computer connected, you can actually, as good as this satellite data, you can look at the solar flares. And why we first time I talk about VLF, solar flare is very definite and very quantitative event. So first we talk about the solar flare is not only thing that we look through VLF, it's the easiest thing or definite things. So when we started like solar flares studying VLF 15 years back, these were the first things we studied. Not only the presence of the flare, but of the quantification. You know, M class means these are the stronger, relative stronger flare. C class is the weaker flare, and all. So for this, we actually observe this quantitative measure. And now I will come to the theory. I will go. Okay. One thing that I mentioned that these signals are not taken from the Indian transmitter in Kanyakumari, which is called VTX. This is another even better quality transmitter, which is called NWC, which is actually located in the western coast of Australia, which is from Kolkata, which is nearly 6,000 kilometers away, like Great Circle path distance. But as I told you that it can travel happily without much intervention, thousands of kilometers. So we happily receive the signal. Just I am coming from our center in Mignapur. Just I am coming back. So in like solar activity, you know that solar maxima is coming up. So these activities are going on. So we are already having a lot of solar flares, and last we also observed, I should mention, in last month of May, we had a like very strong geomagnetic activity. We also detected, I was just saying and I was discussing with my colleagues. So these are the old things I was showing just for that, but we are continuing activity. So this is a kind of measurement that we need to do 24/7. And what is the advantage is that these paths are typically thousands of kilometers long. Kanyakumari is 2,000 kilometers away. Australia is 6,000 kilometers away. Another transmitter is there, which is in, I am not going to show you, which is in Japan, which is almost I think 4,000 kilometers away. So over the long patch, over the path, long patch of the ionosphere we can study, and we can study almost getting the signal free of cost. So that is the main advantage of doing this. So these are, I will not, so this is first one thing, everything I am not going to explain, but this is, you know, the location of the transmitter near the Kanyakumari, and this is our ICSK, our station. So this again, and this black line actually showing the Great Circle path, which is all close to 2,000 kilometers. So while I study this, our VLF signal over this station, we are actually studying the ionospheric profile over the entire 1,000 kilometer propagation path. Okay. So and these are not going to discuss much. These are actually we have. So what is the way? Now I go to little bit of our analysis techniques. So this is, we have one very standard thing, and we also have developed. This is called the long wave propagation model. Long wave propagation model is a theoretical or numerical analysis which actually simulates the signal profile. For example, if we can predict or we can, so what actually it does, it actually we virtually put the transmitter, we put the receiver, and we give the ionospheric conditions, basic ionospheric conditions to the code, and that actually gives us the profile. These are the signal profile that's given, and these technical things I am not going, but these are there. So this you can see, these are one very simple I wanted to show you, that this is amplitude and this is phase, but in the previous slide I was showing the diurnal variation. This is we call the spatial variation. Spatial, you know that if we have a receiver, so we can receive at a single point. But if I get a set of receivers over the entire propagation path, then what should be their profile? So these are at a given instant of time, but the spatial profile. The 0 means the Tx is the signified transmitter, and this is our receiver. So these are interference. In theory we explain this using we call the theory of modal interference. That means that there is the single and multiple modes are propagating through this. Actually, in simple word, this can be explained through the propagation of signal through fiber optics. We know that when fiber optics are core and cavity and core and cladding, so there, what happens is when signal goes through without attenuation and successive multiple total internal reflections for multiple times. Same thing we call it with this theory, we call it the Earth ionosphere vector. That means that you have our Earth and Earth as the lower boundary and ionosphere as the upper boundary, and signal goes through multiple successive reflections and without less amount of attenuation. Of course, there is attenuation and other factors, but overall. So this you can, if you are first time you are getting introduced to this subject, you can compare with the fiber optics communication, but in a different scale. So this is the basic idea of this. So what happens, and very simple thing, what actually this LWPC or this long wave propagation model does is actually solves the Maxwell's equations over this boundary within the condition, numerically of course, and then this gives the quite a good profile of very low frequency signal, how it should be. So this is one of the main tools, and it is one of the main tools through which we connect the very low frequency signal and as well as the ionospheric. Okay, so this is another thing. This is, as you can see, this is our, I am showing you another theoretical simulation. This is basically this point here. This point, this is, I hope you can see the Indian map. This is our transmitter. So what we have actually calculated is that if we simulate at a given instant of time, this is actually for the, as you can see, this line and this line, these are actually the day-night terminators of the sun. So on other side, this is already daytime, and this part is night time, and this we call the spatial profile of the very low frequency. We know that we have signal at different, as you can see the black dots, these are actually our receiver network we have, but we have, this is our completely the numerical model that we have put ionospheric conditions over there and we calculated this profile. So this is the, like, in night time what happens, as I told you, in simple things I told you that in night time we do not have the D region. So we have D region as well as we have the local effects. Local, like nighttime scintillations are there, and the local, for example, local, I will come to that. Local thing means, for example, the seismic effects. So in observation we are familiar to observe the time profile, but simulation enables us to look at the spatial profile. And not only that, maybe I will not be showing all of this, but when we compare the spatial profile with the time profile of different domains, something actually we very well explained. So these are this is basically Indian Center for Space Physics. We have conducted to understand the ionospheric behavior over India. We actually conducted 4-5 VLF campaigns. The campaign means what we have, we bagged the VLF receiver and all this, and we move around to different places simultaneously. And we have, for example, 10 days, 15 days continuous observation. But the interesting thing, we do the observation simultaneously. For example, in this campaign, I was at the point M, which is the University of Kashmir. I was there, and our colleagues and friends, they are other places. So these are, as you can see, this was actually the first. These are the first observation. As you can see, the diurnal profile. But the interesting thing there, this is the picture. After this picture, the subject became more interesting because these diurnal profiles, all are the diurnal profiles, but these are all taken at different locations. For example, you can see A. A means it was taken at some Manipur northeast somewhere, and so eastern profile, western profile, and this diurnal behavior, that is also different at depending on the propagation path and depending on the season. So these become, because previously, before this paper, we actually thought that okay, the diurnal profile is there, it will be uniform all over. But it has a great variation over, and there are many places where we did not get any signal at all, just because the destructive interference of different modes of the propagation. So this is very, that becomes, the subject became more interesting. So these are the general overview that ICSP for the first time they conducted the, I was fortunately part of that, and then there, so one result and there. Now I come to the solar flare. So I should not talk much because Sarah has already talked about solar flare. These are the NOAA observation of a typical the X-ray observation of solar flares. How the X-ray becomes at least 10 to 100 to 1000 times than the average value. So this is the log scale. So this is the case. So now this is okay. However, this picture, this is like how this radiation comes. This is small animation, and this is our observation. So this is a very important picture. So this is what happens that we started, as I am talking that this VLF observation for solar flares and other VLF observation can be used as a very good substitute for the direct satellite observation and ionospheric monitoring. So this, as you can see, this is the both there everything, you can see the N class, C class as well as X class flares, but what you actually can see is that you can observe the two things put together. First is the differential very low frequency amplitude. How the amplitude perturbation takes place. You can see that for X class we have 6 dB of deviation is there, and for example for a C class we have a 2 dB, 3 dB of observation is there for C class. So not only we can feel the presence of the flare, we can actually quantitatively we can measure that how much ionospheric perturbation is taking place during the flare. So this is the one of the main advantages of this subject. Okay, so now what I am not going to much details of this. This is like typically what we measure is things. What I wanted to say in this presentation is first we measure the electron. We started measuring electron density profile. Next we started the response time delay. Means the X-ray response and very low frequency response, those doesn't happen simultaneously. So there have a delay. Also we calculate the effective recombination profile because the ionosphere is kind of chemical factor. So recombination profile is very important. Okay. So now this is the path as I showed. Previously I showed this VTX, and this is the NWC. NWC is a transmitter. It is in the western coast of Australia, and this is our receiver. This red line is actually almost 6,000 kilometers long. So while we are observing this NWC signal in our station, that means we are practically looking at the ionosphere over 6,000 kilometers, and also it has a trans-equatorial behavior. And this, as you can see, that this line, this black line, this is the equator, but this is geomagnetic equator, and this is not a geographical equator. So while this signal is crossing the equator, there is a reversing of the behavior that is being observed. Okay, so this is our theoretical idea of this. I am quickly go through this. And how much time is that? 50 minutes. Okay. So this is actually this is a schematic diagram. This is just to show you FPT is the X-ray flare peak time and APT is the amplitude peak time. So whatever we always observe that during a flare, the maximum of the X-ray and maximum of the VLF that actually does not take simultaneously. They have a time gap. Just because that X-ray is coming and it is doing the ionization business, and every chemical reaction have their own recombination time scale. Some of them have few seconds to some of them as few minutes. So we calculate this as a collective effect of this effective recombination results into this what we have defined as time delay. So now another factor, this is solar zenith angle. I am not going into much detail. Solar zenith, you know that the relative position of the sun with respect to zenith is called the solar zenith. So now this I am not going into much details of that. This is very important. I come to this point. So here you have three solar flares you have taken. So solar flare is one of the main agenda that we have analyzed just to look at the overall property of the ionosphere. The three solar flares you have taken. One is the X class, which is strongest in nature. Another is M, another C is the weaker class. So what we have observed is the amplitude perturbation is taking place is fine. But what we have observed is that the amount of delay that I was talking about, the effective delay, that gets drastically changed for different classes of solar. For example, for the X-ray, delay is matter of seconds, few seconds, mostly the less than 10 seconds. But while study this C class flare, this delay, for example, for 2 minutes to 3 minutes. So this is a drastic change in delay. So what happens is that, for example, for X class, that ionization is much, and in the higher energy scale, the decombination time scale is closer. So that is there. So we have what we actually, so we take a handful of them and we plot it as a function of the maximum flux of the flare, and we see for the first time that the delay profile is actually have a great dependence on this X-ray flux. For stronger class of flares, the delay remains that ion. So what is the bottom line I explained is that for stronger class of flares, the ionospheric response is more instantaneous. For weaker class of flares, we have a longer time, ionosphere take a longer time to respond, but for strong flare, the response time becomes very less. Okay, so and also these are much details, I am not going into that. This again delay that has a secondary dependence on the solar zenith. So a single class solar flare which is happening at the daytime or at the daytime or at the morning and afternoon, they have their different impacts. And we also have a classification out on that. I'm not going much into that. But okay, so there you can have some idea of like for different class of flares, and we segmented into have different time zone of happen. We have bunch of them, and we have calculated this factor of this how they are correlated like through the ionosphere that we have calculated. So okay, so same thing. So I prefer to come to this part. Is that this is actually some effective recombination coefficient. Here also this. Okay, so this first, before going to that, I should explain this equation. This is another very famous equation in our subject. We call it the electron continuity equation. So d and dt is the time profile of rate of change of electron density, and which actually depends on a few important factors. For example, Q is called the effective ionization, and that comes from the directly from solar irradiation and other factors. And lambda is a very interesting parameter which is especially important for D region. That's because lambda is called the relative negative ion to electron number density ratio. So negative ions are, as just to inform you, negative ions are the special things which is unique to D region, mostly unique to D region, and it matters what is the ratio of electron to negative ion number density ratio. That also contribute to this. And also I is an ion-ion recombination, and D is called the dissociative recombination. So effectively in our subject, through the VLF analysis, we could able to calculate this parameter which is called effective recombination. Because so far we have not investigated each and every combination separately, but we actually, as a representative of the chemical property, actually calculated the effective recombination as a whole. So as you can see the results of delay, so we derive, let us look at this formula. We derive this effective recombination as a function of solar zenith angle, as a function of delay. I'm sorry, it is actually delay, but this A maybe some due to format is coming up. So we derive this formula and we use this delay profile from our VLF observation. We took the amplitude perturbation from this profile, and finally we have, these are also our parameters, we have finally calculated, you can look at this parameter. These are the effective recombination as a function of the maximum flux of the flare. So how this recombination, overall recombination behavior in the D region, how it gets affected for different classes of flares, and also other not only recombination, we also calculated the electron density profile also. So it is actually well understood that the electron density content, it will increase with stronger case of flares. So that is another parameter. So okay, so first idea is that okay, so this objective of solar flares are not important, but these solar flares are the useful tools for us which actually enable. So now I should this is another interesting work that when we use this GN4 Monte Carlo simulation. You know, the GN4 simulation which actually takes into account this ionospheric chemistry part. As I told you, ionospheric chemistry, and that this is actually the altitude profile of the electron production rate that we have calculated. So what we have actually do, this is very in situ and fundamental model. GN4 what actually, it actually counts the photons which are coming up from the sun and how it is getting ionized, the different layers that we calculate from the simulations, and as a result we calculate the ionization profile, and from the ionization profile we solve this through our long wave propagation model, and we calculate the VLF. So as a reality, what is actually happening starting from sun to the region ionosphere, we could model using this GLF, and we can actually So these are the set of equations. Okay, these are called the GPI model. GPI means Glukov-Pascoe-Inan model. So as I told you that we have a 6,000 chemical members in the D region. So what it has chosen? It has chosen 4 important members, groups: free electrons, positive ions, negative ions, and cluster ions. So these are the classifications. So they have their independent continuity equations. So what we do, we numerically solve. These are called the GPI. Glukov-Pascoe-Inan, they propose this idea, and so we solve this equation numerically. We get the electron and all ion profiles together, and we put it in our log wave propagation model. We compute the radio frequency and we compare with our observation. So what is actually happening, we could model. And for this Glukov-Inan is of course not exact model. Okay, so it's not good idea to take thousands of species or to just pick up 4. But actually for our VLF, this actually worked very well through the limitation of VLF observation. So we solve these 4 species, and we solve this, and if we compare with VLF, we have a very good observation. Also, as well as we have the understanding of the ionospheric behavior. So these are the different altitude profiles of electron density for different classes of layers that we have calculated after the solution of this kind of equations. And this is very interesting result. These are one of the a few years back, but these are one of the breakthrough papers that we have published, because beforehand we had a very good observation, VLF is fine, but starting from in situ, starting from sun, how much photons are coming, total modeling part that we have did, finally we end up with this. As you can see, this is the dashed line. This dashed line is actually our simulation, and we compare with we actually set our location of the simulation to our station, and we compare with our direct observation. So now we can say, after doing some time, we have a good A to Z, like what is the process, what is happening, of course with some approximations, but we have the understanding. If we have a quantitative VLF, how much VLF signal is happening, VLF signal perturbations are taking place, so we have a good idea of what actually should happen to the region of the ionosphere for such behavior in the area. So that is a theoretical thing we have done. So I do this modeling part mostly, so I am emphasizing over that. So apart from that, if you VLF observation and their profile, they have also different talks can be given. But so modeling is my specialization, so I am coming back to that. That is my problem. Okay. So now another part. So I started with VLF, but this part, another thing that I actually little bit I went away from VLF, and we actually directly tried to solve this equation. Previously we did not solve this equation. We have the electron density as a GPI model, as I told you, and we have this. Now we have this electron continuity equation, and we calculate this ionization from as we have as a source, we have our both satellite observation, NOAA observation, and we calculate this, and these are different quantities. So what we do, I am not going too much, but so what we actually, after VLF, we tried to find out some direct mechanism to solve this electron continuity equation. So what we did, we actually calculate this, look at this equation. So this is a phi. Phi is the X-ray observation, for example, taken from GOES and NOAA. We calculate this ionization profile, we put it in the continuity equation, and also we put it the effective recombination other profiles to that, and we numerically solve this equation. So this was our first attempt in the literature to solve this equation directly, this continuity equation, and get the electron density profile directly out of that. So what we do, this is actually what I said, and so now I should directly go to the results. Okay, so this is our first observation. This is so I started with VLF, but this is some observation is there where we have the blue one is the Bose observation of X-ray, and the red one is the electron density observation, not from VLF but directly from this electron continuity equation. So what we actually do, we from VLF observation we know that the electron density response and the X-ray response have some time delay, but as a direct solution from this continuity equation we are getting the time. So that's why we started with solving this equation. Okay, so this is our definition of time delay. This is the time of peak of the electron density minus the peak time of the solar flare. This is the time delay, and these are we actually done for different classes of solar flares. But okay, so this is very important. Again, new result that we got, that in the x-axis we plotted the day of the year, and y-axis we plotted the time delay. That means, so what we actually assumed, a little bit tricky thing, that we actually assume that if one similar solar flare repeats itself on every day of the year, what will happen to the day? Because in X-ray flare, that actually day to day there are different kind of flare, but we actually assume, for example, a C class flare, an M class flare, and X class flare that repeats itself. So if the ionospheric response will be same or not. So idea is that, so we get as the following is that, so if for example if have and also like so these are actually, if one solar flare is happening, so if the solar flare happens on this part, that will the delay will be, for example, 150 seconds or minutes. Same flare happens if in summer in the northern hemisphere, 60 degree north, N and S are the northern hemisphere. So these are the day of the year variation, as well as we have the like the latitudinal variation. So 60 from 60 north to 60 south. Okay. So now first of all, before going to these details, one thing what I missed to mention is that why I go to this technique, because while we observe very low frequency signal, we have our receiver and we are observation of limitation. So what happens if we do the observation all over the world simultaneously? What will happen? That's why we actually use this shortcut theoretical technique, but the results are very interesting. And same, as I told you that for the northern hemisphere, 1 means the 1st January. Okay, so that actually is very strong seasonal effect. Actually, we observe this in few cases of VLF. So we wanted to have the explanation. So we have it if it in the winter, the delay is much more because the zenith angle is higher and it is slant. And then it is and the summer, in the middle of the year, it is summer in northern hemisphere. It is being same for the same class of flare, same class of C class flare getting low. And on the other hand, if we are going to a southern hemisphere observation, the things are different. So that's why we have the privilege, as I told you, we have a VLF network and all that. We have a delay observation at different stations at the same time. We of course also the delay are not only they are different, they are widely different from one another. So what is the reason we wanted to have some explanation? And similar behavior, these are getting repeated, but these things are higher because this is for delay is lower for X class, this is for M class. These are randomly chosen, don't have to take it very seriously. But however, the class variation, then the delay profile with time, with day, as well as for different latitudes. So this is for global latitude. But one thing is missing here. We actually ignored this part of the equatorial region, and also we have ignored this polar region. Just because the ionosphere is stable and well behaved, and other irregular things are like polar things, and there are like lot of particle outbursts, as Sarah was saying, aurora and all these things. So situation is disturbed. So we have this part. So this is our like one of the this is our actually this is our first paper when with my student. This with different kind of global observation. Many people have like appreciated this part. Okay, so next I'm not going to very much technical detail, that will may be boring for you. However, so now another thing, in the last few slides back I was showing that the delay profile as we computed from VLF. Now if I have it directly, I am solving this continuity equation and getting the profile. What we are doing, we have done this delay for like a different, also the latitude variation for different case, as well as for a huge number of layers. As we have taken the whatever layers are available through the X-ray observations, we get and the delay profile. We actually recheck this profile of delay. For delay is like the delay range is much higher for weaker players, and as is actually they have a different, the patch is getting narrower for higher cases. So this is not maybe a new result, or maybe this is a much extended version of the VLF observation of delay that we have discussed. So these are, I am not going, these are, so just to quantify them, like we have like RMS and slope and few parameters we have calculated, and also we have that from S60 means the south 60 latitude and N60 means the north 60 latitude. So with different latitudes we have calculated the RMS values of this out of this patch. So we have a very regular behavior that when the sun has a greater control on the lower latitudes because of the lower values of solar zenith angle and the what was the idea that VLF, when we are doing VLF, we have the propagation path dependence, because whatever we study, but we are constrained to look at the propagation. So when we had the theoretical idea, why don't we extend our idea? So that is the idea we propagated in this. And that actually is our student, when he started, I said okay, that's keep VLF for the timing stop and then let the theoretical things extend.
That will make it more dynamic from the perspective of the three-dimensional spherical coordinate system.
That's spherical coordinates are already included.
Yes, because here only the latitudinal effect is included.
Yes.
And the corresponding radial quantity.
Yes.
So it would be r theta phi, everything is there.
Yes. It is already included, because then what is the contribution of zenith angle, what is the contribution of
included, but exclusively it can be done.
That's exclusively actually can be done. For example, in this location in Holdi, if I put this the zenith angle dynamic profile as well as the solar value, what is things that we put it and we solve the equation, get the entire profile. Even before we install the station in this place, we can have roughly one very good idea of what we are going to have here, for example. But the interesting thing is that, as I told you, VLF is a 20-kilometer long wavelength. So here we have a the signal profile is not much different from whatever we receive in Vietnam, because it is only like 70-80 kilometers. So it is nothing compared to radio frequencies. So that is it. Okay. So these are again we calculate. I am not matching. So these are the like, as I was telling, the latitude. So we have actually had the differential things. So what is the difference of delay in different latitude, that we have also discussed, and also we have calculated another parameter. We define this parameter delta lat of delta RMS. Means what is the delay at different latitudes? What is the difference and how it difference gets changed with that. So we go into higher order. Second order in terms of this statistical idea. So that is it. But the interesting thing is that we have done actually more than 500 solar flares we take, which is actually maybe difficult for VLF, because VLF has their own limitation. Maybe solar flare is happening, but VLF transmitter is turned off for the time, because they have their own maintenance time. VLF transmitter, they don't care what ionospheric science we are doing. But because they are as soon as their Navy communication purpose is served, they are more than happy. So they don't care. Actually, they may be unhappy with our ionospheric science, but it is a great thing for advantage for us, okay, for scientific community. So, okay. Next, another thing is very interesting observation. As a last part, this is what we have done is the delay, but their altitude profile. as I told you, the deep region is only 20 kilometers thick, thinnest layer in the ionosphere. But what we have observed, that if we go to the literature, which is actually written 50-60 years back, that this, within the 20 kilometers, the presence of different ions are widely varies. For example, if I go to negative ions are actually negligible to the higher altitude. And higher means if we go to beyond 70 kilometers, negative ions are almost absent. But if we look below 70, there are sufficient amount of negative. So lambda factor is a very crucial factor. So what we actually tried to calculate, again we have theoretically, we calculated this for X class, M class and C class, the altitude profile of the decay. Altitude, so what we have actually observed is that this red one, or rather the orange one, is the X-ray observation, and these are the electron density profile at different altitude starting from 60 km to 80 km. So what we have observed very interestingly is that this actually, as we go to the higher altitude, this delay is getting reduced, and at some point we have a switch over. And we actually checked with the chemical components of that. There is actually the different variations of different, that all the parameters, delay and as well as the conductivity, as well as the effective recombination and other lambda, negative ion, all these are contributing to it. So I am showing you the collective result. And this is most interesting, this actually gets repeated for all classes of layers. The switch over of the delta value, the delta measurement of delta. And also these are not measurements, of course, these are not results of our modeling as a part of the numerical solution of the continuity equation. Next one. What is the most interesting, what actually fascinated us is that we did not do explicitly, we did not do anything. We put the different parameters, as Sir was saying, that different latitude and other values, and different altitude parameters, and we just keep on solving the equation. That is giving us, this approach is simple. If we get a better approach, we can, of course, we can do a better investigation of the region. But with this simpler approach, this is a simple thing, simple solution of this equation, we get such beautiful profiles. And these are actually, which are actually not sufficiently in agreement with the chemical results available in literature. So these are the delay, altitude, but these are called, we call it the spatio-temporal profile. In the x-axis we have the altitude, in the y-axis we have the latitude. So this is a continuous profile, but however they have the different variations of the region. Okay, so we just checked it for different hemisphere. We can have a complete different behavior of the region. Okay, so I think that's it. Because actually there are many more. I actually picked up for few results, but this is my like the end of presentation. But one thing for this, because this MTP has title of solar influence, so I concentrated on solar, how the sun is affected. But the scope of very low frequency is much beyond that. For example, you know that earthquakes. Okay, so earthquakes are actually happening. Earthquake is like our lithospheric business. Earthquake has, apparently it had nothing to do with the space scientists. But the point is that when Kobe earthquake happened in 1995 in Japan, then some Japanese groups started, they have their very low frequency observation. 1995 in the University of Electrocommunication, where I was a postdoc over there. Then Professor Hayakawa is a world famous person. He actually started VLF observation, and through VLF observation he not only detected the earthquake, but he actually wrote a paper in 1996 that he actually, at least 4 days before, the unusual behavior was started. It was started. That time, why it is breakthrough? Because the earthquake and lithospheric things were a monopoly to the geologists. So that is the 1990s, it was a breakthrough that seismic things are, of course the space science can put their heads on that. But but it was not easy, even nowadays it is not easy, because there are many different theories of how this lithospheric energy, because earthquake is like a collision of tectonic plates, and the elastic energy comes out of that. How the two elastic things if collide, they actually get better elastic energy release. But how it gets propagated to an altitude of 200 kilometers, that is there are different theories, and there are different groups they don't believe in that at all. But however, there are different theories. For example, most famous is the gravity wave channel. This actually goes through the atmosphere because atmosphere is acoustic medium. So one wave, if it is generated without, of course there is attenuation, but that can go up to altitude. But if I'm talking about this because I am a lower ionospheric scientist. So upper ionosphere they don't care about it. With the investigator at the 500 kilometers, they don't like it. But as I do with the lower ionosphere, okay? So in that case, we actually do with these things. Another thing is another famous channel which is called the chemical channel. Another theory is there, famous theories I am talking about, these are called radon gas. But what I want to deliver is what is the most interesting thing, at least all of them have reported that all of the channels starts working at least few days before the all of these channels. So this is, and also not only the Japanese famous groups, including us, we have also like observation of Nepal earthquake, and a few years back I hope you know that there is a Honshu earthquake in China. So on those cases, in our case, because Nepal and these are not far, so in our case we have actually reported to 5 to 6 days prior response to the earthquake, and also based on that we are having the different theories, but these are there. But I excluded this part in this slide. It was there actually in your presentation, but it was actually I excluded because you have your presentation on solar and other things. But the VLF actually, so now I just to wrap up. VLF is, first of all, is the signal is freely available. Second is it is very long path. Ionospheric observation can be done sitting at your home. You don't have to go to, you don't have an aeroplane and you have to go there. Just sitting at there. Next point is that there are multiple applications. For example, starting from solar flare, and which another thing I excluded it. This is a solar eclipse. Solar flare is the enhancement of ionization. Solar eclipse means the obscuration of the solar disk by lunar disk. So it is a temporary reduction in the ionization profile. So reverse effect ionospheric. So we have already many works on that. Our team, myself and also our team, and they have ICSP team, they have worked. Many results ionospheric reduction is there. Third thing we have actually apart from sun, we have calculated the ionospheric effects of GRBs. GRB means the cosmic gamma ray bars. These are suppose they are assumed to be coming from different galaxies. So they are coming. And most interesting, I should say, most interesting thing is this is nothing to do with sun. These are the seismic effects, the upward energy propagation. So these are, we have sufficient observation of that, and we have also many publications, and like most of the publications are very well cited because nowadays the group is expanding.
Heliosysmic.
Huh?
Heliosysmic.
Not heliosysmic, because helio is sun, helio not. This we call this subject is called LAIC, lithospheric atmospheric ionospheric couple. This idea and different. What basically, if I say what is the problem is that if I say that I believe in chemical model, you will say that I don't believe in chemical model, I believe in gravity wave model. This is the idea, but what is the everyone actually is in agreement with the existence of such very low frequency observation. So we are nowadays like students, as you know that this data is available to us. We have and also many students, physics and also like engineering students like you, and their BTech, MTech projects. At a part of that they are doing small projects. These are the detailed analysis, but however small observation they are calculating the atmospheric things, interesting things, and we have a practice of dealing with the students, and they are doing also these things. So these are also like we have done like different aspects, but these are also open because nowadays SAR is helping us very much. We are coming into these are the numerical modeling, but we are having the machine learning things coming, which are not at all in the subject. So if we have how we can feed this thing and I can improve the atmospheric model, that's also open field. So this is also open field for research, for doing so multidisciplinary. Not only physics, mathematics students, computer students, many of them can come in and they have their research aspirations. So these are the things, and also in this occasion I was trying to show Babu that we are having our observatory in Midnapur. You are also welcome to come. It is not far away. It is near Pashkula. So you can also have an observation and radio frequency live station you can see. So there are interesting things that are going on. So I think again I thank Somo for inviting me, and thank you. It's my pleasure to be here. Thank you. So if you have any questions.
I have one query that the solar flare can be measured by VLF receiver, as you saw the diagram and all those kind of thing. So that solar flare also can be measured by the satellite measurement station. So what is the comment on this matter, that is there any difference of measurement from the satellite or from the ground base, because the signal have to pass all the regions, atmospheric regions.
Yes.
So both are highly correlated, or is there any difference between that measurement and this measurement?
Good question. First point is that satellite observation, direct observation. Their X-ray are coming and they are just catching this X-ray. We have is a completely indirect observation. So the X-ray is coming, it is penetrating all the ionospheric layers, it is ionizing the layer. As it is ionizing the layer, the electron number density, ion density, that gets changed. That actually changing the effective propagation path of the signal. Then the signal gets changed, and as we have a receiver. But this we have with, and this is the observation. So they are not like, method is, one is completely direct and another is completely indirect. But the second part of your question, they are completely correlated. They are completely correlated, because when you have, suppose you have a X-ray which is flare, which is twice of the another one, then their perturbation is also like comparable. For example, if you have a 3 dB of perturbation, otherwise if you have a not exactly maybe double, but it is very close to that. So you can have a, I was talking about direct correlation, linear correlation. So we use linear correlation for that. It is, so that I can tell you for sure that they have, to some extent, linear correlation is valid.
Yes, just to add with this point, that if it is a linear correlation, as Tom was saying, then of course any kind of simulation done with the exactly observed, directly observed from the satellite and this ground-based observation, that will give you similar kind of result. But if there is a high amount of non-linearity, then perhaps we will get different results. In that case, we have to just search for what is the reverse way to understand the connection from the Earth's perspective, how the things are mixing are going on. And if we can deduct that part, then we can do it.
That's I can show you that the GN4 model.
Yes.
From top of the, we started with the counting of photons, and we end up with the simulating the VLF.
Exactly.
To the entire channel. That I don't know how much I could explain, but the thing was like,
Yes, exactly.
that is, and another point that was not a part of your question that I can add, that why I emphasized on looking at the solar flares. Because solar flares are, first of all, we have the direct observation of X-ray. We know exactly what is the time, what is the energy deposited, how much ionization there should be. So these are actually known events. When we have a long experience of doing this science, but when we started, we did not know that what is the VLF change and ionospheric change are correlated. So we started with the solar flares as a tool to understand and simulate this behavior. Because if I start, for example, if we start with the lithospheric things, it is a complete mess. Because things are not linear, as I said, a lot of things are yet to be done in terms of physical modeling as well as mathematical modeling. So this is like, solar flares are well understood things. So from that we actually standardized our simulation behaviors. Which were, for example, continuously available.
In continuation with that, I just have I need your suggestions that currently some of the researchers are putting their effort to predict the solar flares.
Yes.
Because solar flare is completely irregular in nature,
that's true.
but it have a huge effect, because a large solar flare can bring the CME as well.
That's true.
So what is your comment on this, that is the prediction model can works in very fine, that we can predict the solar
First
flare
of all, I should not
accurately?
comment on that, because these are the business of solar physicists. Thank you for your question.
No, my next question is, if yes, then what is your comment on VLF signal? Should a prediction model can be used the VLF signal to predict the solar flare, or it should go for the satellite based direct measurement?
Okay. So first part is that the solar flare prediction is another very interesting science, and this is actually the part of the magnetohydrodynamics, that the simulations are going on, how to predict what are the parameters for the solar flare. Just an example that one of my friends, he is in Princeton University. He is working on the coronal heating, which is another very millions of temperature. Solar surface is only 10,000 kelvins, and suddenly it becomes millions of kelvins. So he is giving some very Alban wells and reflection. He is like he just written a few months ago, and paper immediately became world famous. So that was another very interesting thing. But as you said, that how this effect on the prediction. So for our team, we have not worked in the solar flare prediction itself, not yet. But because if as the solar flare, I don't know, because solar flare happening depends on solar mechanisms. And if solar flare happens, we have the ionosphere. So solely from ionospheric studies, you cannot predict the solar flare. But you can predict the effect of solar flare. For example, today, what in this area today, if we have a solar flare and we do not have VLF observation in this region, for example, in our observatory, so now we are equipped with what should be the, if for example some VLF effect we do not have observation, just assume. So we are equipped with the simulation tools, we can predict what should be the behavior of the VLF observation of the solar flare. We can simulate this one. That is we are equipped with. But prediction of solar flares is a solar business. It's not ionospheric business. So you can understand.
See, what we can say, just a continuation that if I suppose the direct observation of the solar flares than from the satellites or from other issues, this can be supposed as an input. And at this ground level, what the things are observed, this is the after effect, so it can be supposed as an output. Okay. And it is actually supposed to be via some channel, which may be a black box, because we don't know exactly what is happening, but still something is happening regularly, and that's why some output is generated. So if you suppose that output and go for the prediction, that is only for the lower level houses. But if you just want to use the MHD equation and get the satellite observation coming directly, that prediction should be supposed as a purest part of that particular prediction. So that prediction at the beyond the terrestrial cases, and this kind of VLF-based prediction should be for the in-house cases. Though these predictions are different.
To add to your answer, that as you said, input-output, so actually we are now equipped to do the both of the directions. For example, if we do not have VLF observation, we have the X-ray observation and our tool, we can go to the VLF. And if, for example, we have the VLF observation and we can actually, with some errors, with some like the sigma, we can actually generate, we have all, I'm not showing because all results are not possible to include. So we have our mechanism, so we can, with some maybe 20%
that means suppose some satellite results are not available,
yes,
but ground observations are available, yes, we can indirectly interpolate that.
Actually, not enough, actually go through physical mechanism, physical tools we can do, because we have maybe approximate, but we have a complete A to Z model.
The reconstructions.
Yeah, because we started with observation, I started with doing things in 2008. All these things, but then it was only because you know initially you will understand this is the observation based subject.
Now there is
observation, but our director started, okay, observation is enough, everybody is doing observation, you go to the modeling, otherwise you will not get any credibility, because in India hundreds of people are getting the observations, but most of them are not doing any modeling. So from observation they do this and that, and okay, fine. But he first from the day one he started that, okay, observe is no problem, but we have to go to the modeling, otherwise there is no credibility. That's why we have sufficiently, not we, our team, they have, my friends and colleagues sufficiently developed this subject so that they can go to the, like as you said, input and output. So go to the, from output to input and input to output, they can move around. Of course errors are there, they are not perfect, but we can do it.
Yes, that stochastic part is there. If you remove the stochastic part, then reversible.
Reversible.
Yes.
Nowadays
otherwise irreversible. If you consider the stochastic part, then irreversible.
Now with DLR, German Aerospace Agency, they have like worldwide mid-latitude very low frequency observation they have. So we are working with them now because they have a large set of observation, but they are not interested doing their theory because they have observation and they have their tool computational system because they have hi-fi system they have. But theory, so we are much smaller group than because there are a lot of money, a lot of facilities, but we are doing because we are doing the modeling part because otherwise it was not complete.
Commercially, theory is neglected because if theory is available, then you can create the data.
Yes, that is true. That is true. Now that's why we have the different opportunity for collaboration. Because a lot of people recently, last week I went to 70s, this electron continuity equation. What they do, they actually assume some d and dt equals to 0 and they have some linear thing. So when I said that, okay, I started solving this equation and we are getting the profile and delay, and I was discussing in the lunch. So I was telling them, okay, so it was like surprise. Why? We have not solved it in our lifetime. You said you have solved it and doing this and that. So we have a long discussion. So I took a long time to convince her that okay, we are solving and okay, you are more experienced, so you can prove me wrong, no problem. But we are actually getting results, and which are some way, maybe if it is 50% is in agreement with the observation is fine. 100% is impossible target, but it's fine. So because for example is a delay. Also VLF delay was there, and delay how it's changing with the flares, we had the idea. But suppose we don't have like 5,500 VLF observation of solar flare, it is not there. So what we do, we just solve the equation. So did you say that how you put the values from higher to lower with the increasing flux? So I said I did nothing. I just solve the equation, it is automatically is coming out of, and how say the latitude variation, how we are putting manual. So I do not put in manual. These are theories are coming up like that. So like a very nice discussion it was there. So that is the thing. But observation is one thing I must admit. In terms of VLF observation, there are hundreds of people that are 100 times clever than us. But so that's why you consider it a model. And the VLF is a network science. You cannot do it sitting in your home alone. So it's a part of network. If you have more money, who have government organizations, they more money, they prepare this VLF tools and they distribute, and they made their own network, which is not very easy for things for us to do. That's the limitation. So that's why that forced us to move towards the direction of modeling.
Thank you, sir, for your thought-provoking session. In this session, the speaker provided an in-depth analysis of the D-region ionosphere, focusing on how it responds to solar energetic events, particularly solar flares. He discussed the use of sub-ionospheric, very low frequency VLF signal, which is typically between 3 to 30 kHz, as a sensitive tool for monitoring changes in the D region. The speaker explained how these signals can help remotely detect the effects of solar flares and outline the modeling of VLF signatures during different flare classes like C, M and X. He also introduced an alternative approach by solving the electron continuity equation to compute electron density and response time delay profiles during solar flares. Both methods, VLF signal monitoring and electron density modeling, were highlighted as complementary tools for gaining a deeper understanding of the D region's behavior under solar flare influence. Once again, we extend our heartfelt thanks to Dr. Boshak for enriching our knowledge in this field. Now, we would like to express our gratitude to Dr. Boshak for his enriching sessions. To do so, I would like to invite our head of the department, Professor Dr. Uday Maji, to present the token of appreciation to Dr. Boshak. I also request Dr. Maji to present the memento as a symbol of our thanks for his valuable time and knowledge he has shared with us. Dr. Bosha, we are truly honored by your presence today. As we conclude this session, thank you once again to our esteemed speakers and to all the participants. Now, participants, there will be a practical hands-on session led by Dr. Shomo Roy, Associate Professor of AI Department and Coordinator of this FTP. And this session will start around 4 o'clock, and also bring the laptop for this session. And we look forward to your continued participation in the same. Now there is a gentle reminder about the industry visit which is scheduled for the tomorrow at Haldia Energy Limited. And please note that wearing proper shoes is mandatory for safety purpose. So with this note we conclude this session, and I warmly invite everyone to come forward for a photography and to mark this remarkable occasion. Thank you all and enjoy your lunch.